So we almost have the value that we were hoping for. There's just this extra 2 pi. So I want to go back and see how I can manipulate everything we've written so that we can get actually the result that we like. So let's go back to where we were here. So this part is where we just did the definition of the delta function and the integral of m of u. I don't want to make any changes there. But if I don't want to end up with that extra 2 pi that we have below, I want to do something to get rid of this 2 pi. And to get rid of that 2 pi, what that really means is I'm hoping that somehow or other, so I'm just drawing a cloud, this is my idea here, I could get an extra factor of 1 over 2 pi in my expression here somehow. So I want to go through two pieces of the argument. First, I want to show you that if there actually were a 1 over 2 pi here, everything would come out perfectly. And then I will show you how we can get that 2 pi into this part of the expression. So the first piece, if I actually manage to get my 2 pi into here, then that 1 over 2 pi, that 1 over 2 pi, if it's sitting outside my integral here, that will immediately come and multiply by this 2 pi and cancel and give me 1, right? So then I won't have this 2 pi m appearing anymore. That means when I come to the lower portion of my expression, where was he? He was here, right? That when I substituted in for 2 pi of m, remember this came from 2 pi of m of x minus x, x prime minus x, right? That 1 over 2 pi would actually kill this 2 pi and therefore this factor of 2 pi, and then this factor and this factor, and then I would have indeed found a perfect reconstruction of my psi of x, and everything would have worked out perfectly. So you can see then that everything that we've written would still be true, and I would have come to the proper conclusion, provided somehow all we have to do is explain where we could get a factor of 1 over 2 pi in our expression here. Now, looking at this expression, it came, as you will notice, from our intuitions and our guesses. So we definitely have some flexibility here to generate this 1 over 2 pi factor. Now, I could just have made my guess, because remember, this was based on just a proportionality with the probability. I could have guessed that there should have been a factor of 1 over 2 pi in front of this integral that would explain this piece, and then I would be done with my argument. And that's actually one way you can define the Fourier transform and its inverse. It turns out, though, that there's another way to do this that turns out to be more convenient. It will be more convenient because it will help us with our proportionality constants. You notice we were guessing that this probability has to be just proportional to psi tilde squared. If we can make it actually equal to psi tilde squared, that would be great, because then we don't have to worry anymore about this proportionality constant, and we could directly get the probability. So rather than attaching the 1 over 2 pi entirely on this expression, it turns out that what is better to do is to distribute it evenly, symmetrically, between both of these terms. So my psi tilde of k is going to be defined as this quantity divided by the square root of 2 pi. Excuse me, my pen here is giving me a little trouble. Divided by the square root of 2 pi. And then also I have to divide my expression for psi of x by 1 over the square root of 2 pi. If I did this, right, then when I wrote down my guess for psi of x, I would say it's an integral of some weights times this e to the I kx divided by root 2 pi. So there then would have been a divide by square root of 2 pi appearing in this portion of the expression from the first integral. Then when I substitute into the brackets, I, according to this analysis, would have a 1 over square root of 2 pi next to the e to the I kx, minus I kx, I'm sorry. So here I would have then a 1 over the square root of 2 pi. I would have such a factor there. And then, of course, those two factors multiply together, right? And then they would pull out, right, to give me this 1 over 2 pi that then perfectly cancels the 2 pi on my m, so that then I have integral of psi times m and then everything will follow through. My integral psi times m is the analysis we carried out here, which is really psi times a delta function, and that gives me psi. So now all of our mathematical pieces are working beautifully. So this, in fact, is how we will, from now on, define our Fourier transform and our inverse Fourier transform. There's one last piece of slightly mysterious physics to explain, which is, okay, for the inverse transform, it has to be defined in whatever way undoes the transform. That part is clear. What is not clear is why there should be this 1 over square root of 2 pi. But I want you to notice where this comes from, right? When we wrote e to the ikx, that came from de Broglie, right? And we had this basic intuition that pure states of momentum should be e to the ikx. But at that point, we were really dealing with just proportionalities, right? We hadn't defined the normalization or the factor or the size, the amount that should be multiplying our wave. And now we can see that really a pure state of momentum should be represented not purely by this complex exponential, but with an additional factor divided by square root of 2 pi, in order that we be consistent with the math that we've seen, and this then defines the normalization for our pure states of momentum. And that then completes our analysis of the Fourier transform and the connections via the physics to the inverse Fourier transform.